Hello, welcome to SPMM Revision on Demand. In this podcast, I will discuss the concept of evaluating outcomes reported from diagnostic tests. A research team comes up with a new scale to measure depression. This scale is called I-Mood. They are strongly advocating for using the scale as they claim this will improve your diagnostic confidence and benefit your patients. How can you be sure that the scale can be of use? You can test various psychometric properties. These are discussed in a separate broadcast. Of all the various measures, the most important is to establish how well the new scale compares to an established gold standard. This is a measure of concurrent validity. The word concurrent indicates that the two instruments, the new test and the gold standard, are administered together. In other words, two variables are measured at the same time in a sample. Such measurements are often done using a cross-sectional study design where both the test instrument and the gold standard can be applied independently and concurrently to a sample of subjects. Imagine a cross-sectional study of several individuals, some of whom are really depressed on the basis of the gold standard ICD-10, while the others are free of depression. We can expect many patients with depression to test positive for the new test. Likewise, some subjects without depression will also test positive. On the basis of the test results of the two measurements made on each individual, the entire group can now be divided into four cells: depressed patients who test positive, depressed patients who test negative, non-depressed individuals that test positive, and non-depressed individuals that test negative. In this 2 by 2 table, these four groups are plotted. The new test results, test positive and test negative, these are plotted along the rows. Remember, test T for the rows. The disease status, according to the gold standard, is plotted along the columns. Cell A represents the number of depressed individuals that test positive. These subjects represent the true positive group. Cell B represents the number of depression-free individuals that test positive. These subjects represent the false positive group. Cell C represents the number of depressed individuals that test negative. These subjects represent the false negative group. Cell D represents the number of depression-free individuals that test negative. These subjects represent the true negative group. The totals are shown in the last row and the last column. Total number of subjects in this cross-sectional sample is A plus B plus C plus D. A plus C represents the total number of depressed subjects in this sample. B plus D represents the total number of depression-free individuals in this sample. In total, A plus B subjects test positive for the new test. C plus D subjects test negative for the new test. In a diagnostic study, even before the results of the new test are known, there are two definitive groups at the outset. These are the depressed and the non-depressed groups, classified on the basis of gold standard test. How can we describe the characteristics of these groups on the basis of the test results? In this table, A plus C subjects are depressed. Of this, A test positive. The ratio A by A plus C gives the true positive rate, the proportion of disease subjects who test positive. This is called sensitivity. It answers the question, how good is a test in picking up the disease among the deceased? B plus D are depression free. of this, D were correctly identified by the test, that is, test negative. The ratio D by B plus D gives the true negative rate, the proportion of disease-free subjects who test negative. This is called specificity. It answers the question, how good is the test in excluding the disease among the healthy subjects? You might have noted that both sensitivity and specificity are true rates. Sensitivity is true positive rate, while specificity is true negative rate. What is the difference between sensitivity and specificity? A very sensitive instrument picks up the disease even with the slightest evidence. Imagine 10 subjects, only 2 are really diseased. A very sensitive instrument will show a positive result for many subjects, as it detects the illness even with slightest evidence. By doing so, it makes more false positive inclusions. The mnemonic SNOUT refers to the fact that a highly sensitive test, if negative, helps to rule out a disease confidently. On the other hand, a very specific instrument picks up the disease only if there is a strong evidence for the presence of the disease. In this set of 10 subjects, a very specific instrument will show a positive result in very few, as it detects the illness only if there is a convincing evidence. By doing so, it produces more false negative exclusions. The mnemonic SPIN refers to the fact that a highly specific test, if positive, helps to rule in a disease confidently. Lowering the cutoff for diagnosis in an instrument will make it more sensitive, as more positive results are now present, but this will make it less specific. So we need a trade-off where these two values are in balance. This can be found using an ROC curve. ROC curve is discussed in detail in a separate vodcast. Another important metric we can get from the 2x2 table is accuracy. Accuracy is the number of times we get something right divided by the number of times we attempt it. In other words, all correct hits divided by total number of hits. This can be expressed as true positive plus true negative divided by the total population. In this 2x2 table, accuracy is given by the values on the diagonal. A plus D divided by A plus B plus C plus D will give you the value of accuracy. At this stage, it's important to note that all the three values, accuracy, sensitivity, and specificity, do not depend on prevalence. In other words, these are the attributes of the diagnostic instrument, not of the sample on which the instrument is tested. Now, a patient is not worried about how good or bad a test is. He or she is usually more worried about what does it mean to have a positive or a negative test result. For example, does a positive test result mean he or she has the disease? This can be answered using predictive value of a test. Positive predictive value, PPV, informs the chance of having the disease if an individual is testing positive. PPV is given by true positive divided by total test positive. In the table shown here, true positives are A. Total positives are A plus B. A by A plus B gives the positive predictive value. PPV is also called the post-test probability of a positive test, as it is the probability of the disease after someone tests positive. Negative predictive value, NPV, informs the chance of not having the disease if somebody is testing negative. NPV is given by true negative divided by total test negative. In the table shown here, true negatives are D, total negatives are C plus D. So D by C plus D will give you the negative predictive value. Unlike sensitivity and specificity, PPV and NPV are affected by prevalence. As prevalence rate increases, so does positive predictive value. On the other hand, with increasing prevalence, negative predictive value decreases. This is shown in the figure here. Consider this example. A diagnostic checklist for diagnosing psychopathy is highly likely to suggest the presence of psychopathy if a positive result is found among a population of prisoners, than compared to a population of training doctors, for example. So, increasing prevalence will increase PPV. Tests often do not give clear positive or negative results, so we often need multiple diagnostic tools to diagnose a single condition. An important question to ask from each diagnostic test is the likelihood by which the presence of the disease increases in someone after they show a specific test result. To answer the question, how much more likely is a positive test to be found in a person with the condition than in a person without the condition, we need to know the likelihood ratio of a positive test. To answer the question, how much more likely is a negative test to be found in a person without the disease compared to a person with the disease, we need the likelihood ratio of a negative test. Let us now see how to calculate LR positive, that is, likelihood ratio of a positive test. LR positive is given by the likelihood of testing positive in the diseased divided by the non-diseased. That is, the ratio of testing positive correctly divided by incorrectly. In this 2 by 2 table, A people correctly test positive out of A plus C with the disease. So A by A plus C, nothing but the sensitivity, will give us the numerator for likelihood ratio of positive test. Similarly, B refers to the number of people who incorrectly test positive out of B plus D who do not have the disease. So B by B plus D will give us the denominator for the LR positive ratio. This is nothing but 1 minus specificity. So we can calculate LR positive using the formula sensitivity divided by 1 minus specificity. This is given by A by A plus C divided by B by B plus D. Let us now see how to calculate LR negative. LR negative is given by the likelihood of testing negative in the diseased divided by the non-diseased. In the 2 by 2 table, C people incorrectly test negative out of A plus C with the disease. So the likelihood of testing negative in the disease is C by A plus C. This is same as 1 minus sensitivity. This will give us the numerator for LR negative. D people correctly test negative out of B plus D without the disease. So the ratio D by B plus D will give us the likelihood of testing negative in the non-diseased. This is same as specificity. So LR negative can be rewritten as 1 minus sensitivity divided by specificity. In other words, C by A plus C divided by D by B plus D. For both likelihood ratio calculations, sensitivity is always in the numerator. A negative sign in the numerator, that is, 1 minus sensitivity, is used if you are computing the negative test's likelihood ratio. The second point to remember is that the optimal cutoff, the best balance between sensitivity and specificity in an ROC curve, gives the highest likelihood ratio as well. Thirdly, an LR positive value of greater than 10 or LR negative value of less than 0.1 are strong indicators of the utility of a test. Note that prevalence is nothing but the pre-test probability. The chance of finding a diseased person without applying any tests. This is given by the prevalence of the condition in a population. So prevalence can be called pre-test probability. PPV, which is nothing but post-test probability, or the positive predictive value, it varies with prevalence. We have seen this previously. The PPV from a study may not be directly applicable to your patients because of the variation in the prevalence rates between your population and the sample in which the study was conducted. So you need to obtain new PPV values. You can get these by using a likelihood ratio nomogram. An example of a likelihood ratio nomogram is shown here. If you know a specific pre-test probability value, that is the prevalence in your population, and if you know the likelihood ratio of a positive test from a test result, you can calculate the post-test probability that is applicable to your clinical sample. Nomograms are discussed in detail in another podcast. Now, let us see an example. A study assessed the usefulness of CAGE in identifying patients with alcohol dependence. If the criteria for defining alcohol dependence is answering yes to at least 3 questions, look at the table given here and answer what is the sensitivity of CAGE. Remember, this is not a standard 2x2 table. In those who have reference standard positive, number testing positive using 3S cutoff is 4 plus 5 equal to 9. So these are the true positives. These are people who have the reference standard positive, and they also have CAGE questionnaire test positive if we apply a cutoff of 3. To calculate sensitivity, we need true positive number and the number of total number of people who are diseased. So the true positives is given by number 9, and the total number of people who are diseased is given by the number 25. These are the number of people who have the gold standard positive and are alcohol dependent. So the number 9 by 2 by 5, which is equal to 36%, will give you the answer for sensitivity. This is another example. From this table, calculate the value of accuracy. Accuracy is calculated using the diagonal. It's the number of correct values divided by total number of observations. As you can see, 11 subjects are testing positive for the gold standard test, which is the DSM-4 depression test, and they're also testing positive for the screening question. So these are true positives. 40 patients are testing negative for the screening instrument, and they don't have depression as well from the gold standard. So these are true negatives. If we add 11 and 40, the two true values, and divide it by 74, the total number of people in the sample, we will get the value of accuracy. Now it's time to ask yourself a few questions. Thank you for choosing SPMM course for your revision.